Okay, so let's look at some Punnett squares and get used to working with those. This is an example that I looked at in the previous video where we talked about two people with brown eyes, but maybe unbeknownst to them, they're both heterozygous, meaning they're carrying the brown-eyed allele and the blue-eyed allele. And what happens if they become parents together? The way that we would normally set this up is we draw what we call a Punnett square, which is a graph or a table of all of the kids that these two parents could possibly have. So kids are going to go in the middle of here. And the way you start this off is by putting every combination of alleles or gametes, as in sperm cells or eggs, that you could get from one parent on one edge and the ones that could come from the other parent on the other edge. It doesn't matter which side they go on. It doesn't. There's no male or female side to any of this, so you can put the parents wherever you like. It doesn't matter. And so when we set this up, we'll say this is the dad. Dad carries two alleles, big B, little b, and the law of segregation says that he only gets to pass on one of them, which means he may pass on the big B. In other words, half the sperm cells he produces will have the big B allele in them, and the other half will have the recessive little b allele in them. So this will be the dad's side. He'll pass on one of those two things. On the mom's side, the eggs that she produces are exactly the same. They can contain either her dominant big B allele or her recessive little b allele. And now every square in this Punnett, every every cell in the Punnett square represents a combination of the sperm cell on its left and the egg above it. So this one comes from big B with big B. And so this is a kid whose genotype would be big B, big B. Here we're getting big B from dad, little b from mom. Remember, you write the capital letter first if there is one, or the dominant first, so big B, little b. Down here we have little b from dad, big B from mom, but we don't care which parent they came from. We always put the dominant first. So we'd still write big B, little b. In other words, genetically, it makes no difference which parent contributed the big B and which one the little b. On the Punnett square, we don't care, and it's not going to matter for the eye color either. Down in this corner, we have little b from dad, little b from mom, and so this kid is little b, little b. No dominant at all. So these are the genotypes of the four kids that they could have. They could have, remember the names for these? Homozygous dominant. Over here we could have homozygous recessive, or there's a couple of ways that they could have a heterozygous kid. So those are their genotypes. What about phenotypes? What would these kids actually look like? Big B is brown eyes. Big B, little b is also brown eyes because the brown allele dominates. And the same thing here. And little b is the only way that you can get blue eyes. So those are the four possible outcomes, or kind of three possible outcomes because the ones in these two corners are indistinguishable. They're both big B, little b, and they're both brown-eyed. We could ask you to just do the Punnett square and show us everything that's in it. What we usually do, though, is we ask you about the ratios for each of these things. Like, what is the chance that a person will have, that one of their kids will have brown eyes relative to the chance of them having blue eyes? Well, there's one, two, three ways that they could have a brown-eyed kid versus only one way that they could have a blue-eyed kid. So you could say that the brown to blue ratio is 3 to 1. 3/4 of their kids will have brown eyes, 1/4 of their kids will have blue eyes, or that's the chance for each of their kids. Every one of their kids has a 3 in 4 chance of having brown eyes and a 1 in 4 chance of having blue. Because we're talking about the phenotype here, we call this the phenotypic ratio, which is kind of an imposing term, but it just means count up the number of each phenotype and put them in a list. In this case, brown to blue, 3 to 1. Now, if we can do this for phenotypic ratios, you won't be surprised to hear we can also do it for a genotype or a genotypic ratio. And now, instead of counting brown and blue, we're going to be counting heterozygous, homozygous, things like that. We can do genotypic ratios. Here, the possibilities for genotype are big B, big B. So I could say there's one big B, big B. There's two ways you can get big B, little b. Big B, little b. Or there's one way we could get little b, little b. You could express it like this, or I'm not going to write this because it takes up a lot of space, but you could say you have 1 homozygous dominant to 2 heterozygous to 1 homozygous recessive. So asking questions about these, they'll often say, like, for these two parents, calculate or determine the phenotypic ratios and genotypic ratios. They can ask for either one. And then you have to do a Punnett square like this, work out this information for each of the kids, and then count them up. So that's a basic example, and in the next videos we'll do a bunch of examples, work through them, just the same procedure over and over again, and hopefully that will help you to get used to it.